Now we have another concept related to the special matrix. Here it is bordered Hessian matrix. In the case of a bordered Hessian matrix, it is little bit different from the Hessian and higher order Hessian matrix. How? In the case of a Hessian matrix and higher order Hessian matrix, we said that we are optimizing given function without constraint. Constraints illade, that is unconstrained optimization കേസിലാണ് നമ്മൾ എന്ത് ചെയ്യുന്നത് ഹെസ്സിയൻ മെട്രിക്സും അതുപോലെ തന്നെ ഹയർ ഓർഡർ ഹെസ്സിയൻ മെട്രിക്സും നമ്മൾ യൂസ് ചെയ്യുന്നത്. ഹെസ്സിയൻ മെട്രിക്സ് യൂസ് ചെയ്യുന്നത് 2 ഇൻഡിപെൻഡന്റ് വേരിയബിൾ ഉണ്ടാകുമ്പോൾ ഹയർ ഓർഡർ ഹെസ്സിയൻ മെട്രിക്സ് ഉപയോഗിക്കുന്നത് മോർ ദാൻ 2 ഇൻഡിപെൻഡന്റ് വേരിയബിൾ ഉണ്ടാകുന്ന സമയത്ത്. അപ്പോൾ ഇവിടെ നമ്മൾ യൂസ് ചെയ്യുന്നത് ബോർഡേഡ് ഹെസ്സിയൻ മെട്രിക്സ് എന്നുള്ളതാണ്. ഇവിടെ നമ്മൾ ബോർഡേഡ് ഹെസ്സിയൻ മെട്രിക്സ് ഉപയോഗിക്കുക when we have an optimization problem with constraint or constrained optimization. Whenever we have a constrained optimization, then generally we are using a bordered Hessian matrix. So what actually the bordered Hessian matrix it is, then what are the various conditions, and accordingly how we are going to optimize the function. See, we have an objective function, that means we want to maximize profit, we want to maximize output, we want to maximize revenue. So whatever we want to optimize the function, that is generally known as it is objective function. For example, I am writing a function that is the given function which is the function of x and y. We have a 2 independent variable x and y, and this have a objective function. This objective function എന്ന് പറയുന്നത് പൊതുവെ നമ്മൾ എടുക്കുന്നത് പ്രോഫിറ്റ് ഫംഗ്ഷൻ ആയിരിക്കാം, അല്ലെങ്കിൽ കോസ്റ്റ് ഫംഗ്ഷൻ ആയിരിക്കാം, അല്ലെങ്കിൽ ഔട്ട്പുട്ട് ഫംഗ്ഷൻ ആയിരിക്കാം, അല്ലെങ്കിൽ ടോട്ടൽ റവന്യൂ ഫംഗ്ഷൻ ആയിരിക്കാം, അല്ലെങ്കിൽ ആവറേജ് കോസ്റ്റ് ഫംഗ്ഷൻ ആയിരിക്കാം. എക്കണോമിക്സ് ഞങ്ങൾ ഇതുപോലെയുള്ള ഒരുപാട് ഫംഗ്ഷൻസ് നമ്മൾ ഓപ്റ്റിമൈസ് ചെയ്യാറുണ്ട് അല്ലേ. ഫോർ എക്സാമ്പിൾ, ദിസ് ഈസ് ദി ഓപ്റ്റിമൈസിംഗ് ഫംഗ്ഷൻ. വി ഹാവ് എ ഗിവൺ ഫംഗ്ഷൻ ദർ. Then we have a constraint also. See, constraints are given with another function that is g of xy, f of xy, and we have a g of xy which is equal to k, and this is constraint. See, we can easily understand the objective function and constraint. We want to purchase 2 commodities. Consumer behavior നമ്മൾ പഠിച്ചിട്ടുണ്ടാവും. We want to purchase 2 commodity, that is commodity x and commodity y. In order to purchase the commodity x and y, we have a limited income. The income is very limited. The price of commodity is given. The income of the consumer is also given. Then how to optimize, that is how the consumer is going to maximize the utility. So utility maximization will become one of the objective function subjected to the constraint. What is the constraint? Budget line. നിങ്ങൾ ബജറ്റ് ലൈനെ കുറിച്ച് പഠിച്ചിട്ടുണ്ടാവും. എന്താണ് ബജറ്റ് ലൈൻ? ബജറ്റ് ലൈൻ എന്ന് പറഞ്ഞാൽ നമ്മുടെ ഗിവൺ ഇൻകവും കമ്മോഡിറ്റിയുടെ പ്രൈസും തന്നു കഴിഞ്ഞാൽ നമ്മുടെ യൂട്ടിലിറ്റി മാക്സിമൈസ് ചെയ്യുന്ന ഒരു സിറ്റുവേഷനാണ്. സോ ബജറ്റ് കൺസ്ട്രെയിൻ എന്ന് പറഞ്ഞാൽ നമ്മുടെ ലിമിറ്റേഷനാണ്. സോ ഒരു ഫംഗ്ഷൻ തന്നുകൊണ്ട് അതിൻ്റെ കൺസ്ട്രെയിൻ തന്നുകൊണ്ട് ഓപ്റ്റിമൈസ് ചെയ്യാൻ പറഞ്ഞു കഴിഞ്ഞാൽ നമ്മൾ അതിൻ്റെ ഓപ്റ്റിമൈസ് ചെയ്യുന്ന രീതിയാണ് നമ്മൾ ഇവിടെ ഡിസ്കസ് ചെയ്യുന്നത്. അതിൻ്റെ ഭാഗമായിട്ടാണ് ഒരു കണ്ടീഷനാണ് ശരിക്ക് എ ബോർഡേഡ് ഹെസ്സിയൻ എന്ന് പറയുന്നത്. നമ്മൾ ഈ ഒരു ബോർഡേഡ് ഹെസ്സിയൻ മെട്രിക്സ് മാത്രമാണ് ഇവിടെ നമ്മൾ ഡിസ്കസ് ചെയ്യുന്നുള്ളൂ. ശരിക്കും നമ്മൾ constraint optimization മറ്റൊരു വീഡിയോയിൽ നമ്മൾ പിന്നീട് ഡിസ്കസ് ചെയ്യും. See here, we have an objective function as in the earlier example we have a utility function. For example, ഒരു utility function തന്നിട്ടുണ്ട്. ആ utility function നമുക്ക് maximize ചെയ്യണം. At the same time which is subjected to the constraint തന്നിട്ടുണ്ട്, limitations തന്നിട്ടുണ്ട്. So g of xy. So here in the case of a utility function, the budget line will become the constraint. So in that particular case we are introducing a new term. That term is known as it is lambda, and this lambda is known as it is Lagrange multiplier. We are going to integrate objective function with constraint by using Lagrangian multiplier. It is the Lagrangian multiplier. So how we are going to formulate a function? See, we are going to formulate a new function, that is function of x y pi, or it is lambda. Sorry. This particular function, that is new function is formed, that is the function of x, y and lambda, and which is integrating, that is objective function we are writing plus then lambda into the objective function. This new function will be created, and actually we want to optimize this new formulated function. So accordingly, after formulating this optimizing function, new function, first we are going to take the first order condition. That means we are going to differentiate this particular function partially with respect to x, f of x, and equating with the 0. then f of y and equating with the 0, then with lambda and equating with the 0. So this is the first order condition. That means we want to partially differentiate the function, given new formed function, with respect to concerned three variables, that is x, y and lambda. After taking the first order partial derivatives, we have to equate with the 0, and accordingly we have to calculate the value for x, y and lambda, and these values are nothing but it is the critical values. See, after that, the second order condition, that is the most important one, especially for discussing here, bordered Hessian matrix. See, the bordered Hessian matrix, which is generally denoted, that is by taking one constant here, that is it is bordered Hessian determinant. It is bordered Hessian matrix, also bordered Hessian determinant as well. See, it is the determinant that is composed of all second order partial derivatives. Of course, it is also related to the second order partial derivatives, but a little bit difference between Hessian and higher order Hessian matrix. See, will be composed of, this bordered Hessian matrix is composed of second order direct partial derivatives on the principal diagonal, and second order cross partial derivatives are off principal diagonal, which is bordered by, that is bordered by the first derivatives of the constraint with 0 on the principal diagonal. This is the condition. See, in this particular theory version it may be very difficult to understand, but if you go for differentiating or forming with a matrix, it will be very easy. See here, what is saying, we are going to take the second order direct partial derivatives on the principal diagonal and second order cross partial derivatives on the off principal diagonal, bordered by the first order derivatives of constraint. So here I am writing the second order condition, that is bordered Hessian. See, this is, I am denoting bordered Hessian, which is also equal to H2. See, f of xx, that is second order partial derivative, second order direct partial derivative, that is on the principal diagonal f of xx and f of yy, then f of xy and f of yx on the off principal diagonal. So we have a 2 into symbol Hessian matrix. It is plain matrix, 2 by 2 matrix, f of xx, f of xy, f of yx, f of yy. But this is bordered by, see, this is bordered by the first order derivatives of constraint with respect to x, with respect to y, then with 0 on the principal diagonal. See here, 0 is given. So this is in this way you can formulate a bordered Hessian matrix. So how the bordered Hessian matrix is differ from the Hessian matrix? See, it is bordered by, this is symbol Hessian matrix, which is bordered by the first order partial derivatives with respect to x and y of a given constraint. So this is the Hessian, bordered Hessian matrix. Now, on the basis of this bordered Hessian determinant value, we can interpret the result. See, if the Hessian determinant is less than 0, then it is the condition for minimum. If Hessian matrix is greater than 0, then it is the condition for maximum. This Hessian matrix is also denoted in terms of the H2 because it is 2 by 2 matrix, which is mainly focused, which is bordered by separately with the first order derivatives of the constraint. So now this is the bordered Hessian. Of course, the bordered Hessian will be utilized when we have a given objective function which we want to optimize subjected to the given constraint. So here, if you go for taking the generalized bordered Hessian, that means if we have more than 2 variables. For example, see, we have more than 2 variables, then the bordered Hessian will become, see, f of 1, 1, f of 1, 2, up to n derivative. Then bordered by g of 1, that is the first order derivative with respect to constraint, with respect of constraint. Then similarly up to n. So this will be, a complicated case, especially the generalized bordered Hessian matrix. By looking at the determinant value, see, here h is, we can extend, bordered Hessian can be extended to the n numbers of variable, n numbers of the variable. See here, h2, h3, h4, that means the bordered Hessian 2, bordered Hessian 3, bordered Hessian 4, up to bordered Hessian n. Its determinant value is less than 0. See, what is h2, bordered Hessian 2? This is the determinant value of 3 by 3, what we are already explained. Then h3 also less than 0, h4 is also less than 0, then it is the condition for the minimum. This is a generalization. Okay. So now if we have H2 is greater than 0, bordered Hessian is greater than 0, bordered Hessian 3 is less than 0, bordered Hessian 4 is greater than 0. See, we have an alternative signs. It is the condition for the maximum. So we will explain with the example so that it will be more clear. But in our example, we are going to consider only two variables, that is x and y. But in the case of a generalization, കഴിഞ്ഞ UGC example ചോദിച്ചൊരു ചോദ്യമായിരുന്നു ഈ ഒരു bordered Hessian generalized form-നെ കുറിച്ച്, especially conditions for maximization and minimization. I will show you that particular question at the end. Before that, we are going to take one example related to the optimization of a objective function which is subjected to the given constraint. Now we are going to consider one function, that is we want to optimize the function, that is z is equal to 4x square minus 2xy plus 6y square. This is the optimization function, or we can call it is an objective function. But this objective function is subjected to the constraint. What is the constraint given here? This is the subjected to the constraint of x plus y is equal to 72. X plus y is equal to 72. So now we want to optimize this given function. So in this particular case, we are generally known as this function as it is an optimization of constraint. That is constraint optimization. It is a constraint optimization. See here, this is the optimization function I am writing here. First step, we are going to set the constraint equal to 0. We are going to reframe this constraint equal to 0. How we are going to take the constraint equal to 0? Taking x plus y into the right side. So it will become, and equating with the 0. So it will be 72 minus x minus y, and then equating with the 0. So 72 minus x minus y, which is equal to 0. Then we are going to form a new function. That function is equal to objective function plus. See, what is objective function? That is 4x square minus 2xy plus 6y square plus, I am adding plus, then we are introducing the Lagrange multiplier, that is lambda. Lagrange multiplier lambda we are adding here, multiplied by the constraint, that is 72 minus x minus y. So you should be very careful how we are going to form this particular function. So the new function we are formulating by considering the objective function, this is objective function aanu. Adinte kude we are introducing a term, that is lambda, and this lambda is known as it is Lagrangian multiplier. We will discuss what actually the importance of Lagrangian multiplier as well. See, 72 minus x minus y constraint. So now after forming this particular new function, see, we are going to differentiate this particular function partially with respect to x, with respect to y, and with respect to lambda as well. See, first we are going to take with respect to x. If we are going to take partially with respect to x, the derivative of 4x square is equal to 8x. The derivative of minus 2xy, keeping y term is constant. So the derivative of x is equal to 1. So 1 into minus 2y, which is equal to minus 2y. Then here we have a x term also. It is minus x, but it is multiplied by lambda. What is the derivative of minus x, which is equal to minus 1? Minus 1 multiplied by lambda, so it will be minus lambda. And then I am equating with the 0, which is equal to 1. Now, we are going to take the partial derivative with respect to y. See, here we have y term, keeping the x term is constant, the derivative of y is equal to 1. So it will be minus 2x. Then we have y term, which is equal to 12y. Then here we have minus y, the derivative of minus y is equal to minus 1, multiplied with the lambda, which is equal to minus lambda, which is equal to equating with the 0, and this is denoting in terms of equation number 2. Thirdly, we are again differentiating this particular function with respect to lambda. Where is lambda? Here there is no lambda value. Here we have lambda, lambda 72 minus lambda x. If you go for multiplying it, lambda 72, lambda minus x, lambda minus y, minus lambda y. So then if you go for differentiating it, then it will be equivalent to the 72 minus x minus y, because we are going to differentiate with respect to lambda. So it will become 72 minus x minus y, which I am equating with the 0, and this is I am giving as third equation. See, we have a three equations with respect to partial. These are the partial derivatives with respect to x, with respect to y, and with respect to lambda. After that, this is the first order condition. After that, we are going to find the critical values. See, find first order condition we are given here, and three partial derivatives are given here. Then after that, we have to form the second order condition for bordered Hessian. ഞാൻ ഇവിടെ ശരിക്ക് constraint optimization അല്ല ഡിസ്കസ് ചെയ്യുന്നത്, അത് നമ്മൾ മറ്റൊരു വീഡിയോയിൽ ചെയ്യും. അതിൻ്റെ മുന്നോടിയായിട്ട് നമ്മൾ ഇവിടെ ചെയ്യുന്നത് bordered Hessian കുറിച്ച് മാത്രമാണ്. Okay, so after this particular first order condition, see, we have to find the value for x, y and lambda, that we will discuss separately. But here, after the first order condition, we are directly going towards the second order condition because we are mainly focusing on the Hessian, bordered Hessian determinant. See, the second order condition which we are actually framed on the basis of bordered Hessian matrix. So first we are going to create here bordered Hessian. We are already discussed what actually the bordered Hessian it is. It is the second order direct partial derivatives and cross partial derivatives are given here, where direct partial derivatives are on the principal diagonal and off principal diagonal we have a cross partial derivatives bordered by the first order derivative with respect to x of constraint with respect to y, then in the diagonal element, principal diagonal, we have a 0 value. Now we have to find all these values from here because zx given, so zxx or f of xx both are same. So here I am going to take the zx with respect to x, that will become 8, zx with respect to y, which is minus 2. Then we are going to take the partial derivative of constraint. Constraint എന്തായിരുന്നു നമ്മുടെ 72 minus x minus y. If you go for taking the partial derivative with respect to x, which is equal to minus 1, then f of yx minus 2, f of yy which is equal to 12, then we have differentiating with respect to g of y which is equal to again minus 1, then again here it is minus 1, so here also that is, it is bordered by the first order derivatives of the constraint. So in this way you can frame the bordered Hessian. Now we want to find the determinant value of the bordered Hessian. See, if the determinant value is less than 0, then it is minimum, then if it is greater than 0, then it is maximum. So here we are find the Hessian determinant value. See, Hessian determinant value, first we are going to take the first element, that is 8, deleting the concerned column and row, then what is remaining here? 12 minus 1, minus 1, 0, then 8 into 12 into 0, which will become 0, then minus 1 into minus 1, which is equal to plus 1. So minus plus, which will become minus again, 8 into minus 1. Then we are going to take the second element minus 2, it will become plus 2, crossing the concerned column and row. Then minus 2 into 0, that will become 0, minus 1 into minus 1, which is equal to minus 1. So here it is 2 into minus 1, third element into crossing concerned row and column. Then minus 2 into minus 1, which will become plus 2. Then minus 1 into 12, which is equal to minus 12, which is equal to plus 12. So if you go for simplifying it, then its determinant value will be minus 24. Minus 24, which is equal to less than 0. So if bordered Hessian determinant value is less than 0, then this is the condition for the minimum. This is the condition for the minimization. So in this way, see, by looking at or creating the second order condition, that is bordered Hessian, and looking at the bordered Hessian determinant value, we are actually determining whether given function is minimum or maximum. See, in the last exam, കഴിഞ്ഞ എക്സാം 2024 എക്സാമിൽ വന്നിട്ടുള്ള ചോദ്യമാണ് related to the Hessian matrix, especially the bordered Hessian determinant. See, if we have a objective function involving n variable, നമുക്കൊരു ഒബ്ജക്റ്റീവ് ഫംഗ്ഷൻ ഉണ്ട് ഇൻവോൾവിംഗ് n നമ്പർ ഓഫ് വേരിയബിൾ. എത്ര വേരിയബിൾ ഉണ്ട് ഇവിടെ കൊടുത്തിരിക്കുന്നത്? അപ് ടു n, x1 x2 x3 up to n. This is the objective function. Utility function is given, which is the which is the function of x1 x2 x3 up to xn subjected to. See, ഇവിടെയാണ് ഈ ക്വസ്റ്റ്യൻ്റെ ഡിഫറൻഷിയേഷൻ വരുന്നത്. ഹെസ്സിയൻ ഡിറ്റർമിനൻ്റ് ആണോ, ഹയർ ഓർഡർ ഹെസ്സിയൻ ഡിറ്റർമിനൻ്റ് ആണോ, ബോർഡേഡ് ഹെസ്സിയൻ ആണോ ഉപയോഗിക്കേണ്ടത് എന്നുള്ളത് ഈ ക്വസ്റ്റ്യൻ നോക്കിക്കൊണ്ട് നമുക്ക് ഫൈനലൈസ് ചെയ്യാൻ പറ്റും. ഇറ്റ് ഈസ് സബ്ജക്റ്റഡ് ടു ദി കൺസ്ട്രെയിൻ എന്താണ്? ഇറ്റ് ഈസ് 5 ഓഫ് x1 x2 x3 up to xn. സോ ഇവിടെ സബ്ജക്റ്റഡ് ടു ദി കൺസ്ട്രെയിൻ ആയതുകൊണ്ട് തന്നെ ഇറ്റ് ഈസ് കൺസ്ട്രെയിൻഡ് ഓപ്റ്റിമൈസേഷൻ്റെ ഒരു ഉദാഹരണമാണ്. കൺസ്ട്രെയിൻഡ് ഓപ്റ്റിമൈസേഷൻ്റെ സെക്കൻഡ് ഓർഡർ കണ്ടീഷൻ ആണ് ഇവിടെ ചോദിച്ചിരിക്കുന്നത്. സെക്കൻഡ് ഓർഡർ കണ്ടീഷൻ ഫോർ എക്സ്ട്രീമം മീൻസ് ഇറ്റ് ഈസ് മാക്സിമം ഓർ മിനിമം. സോ സെക്കൻഡ് ഓർഡർ കണ്ടീഷൻ എന്താണ്? ശരിക്കും ഇറ്റ് ഈസ് bordered Hessian. That's bordered Hessian because it is the given objective function we want to maximize or we want to optimize subjected to the given constraint. So we have 4 or 5 options are given here. See, what are the options? For maximum, H2 is less than 0, H3 is less than 0. For maximum, H2 is greater than 0, H3 is less than 0. For maximum, H2 is less than 0, H3 is greater than 0. For minimum, H2 is less than 0, H3 is less than 0. For minimum, H2 is greater than 0, H3 is greater than 0. And we want to pick up those answer which is actually given the option. See, it is question is extremum. Sorry. It is the question related to the extremum. That means both maximum and minimum we want to consider. So we will have some options from here. One is from the maximum, another one is from minimum. So how we are going to consider here? We know the condition for the optimization, especially by considering the bordered Hessian, because it is a given objective function subjected to the constraint. So we have to use a bordered Hessian matrix. കഴിഞ്ഞ എക്സാമ്പിൾ ചോദിച്ചിട്ടുള്ള ചോദ്യമാണ്. അപ്പോൾ ഈ ഒരു bordered Hessian area എന്നുള്ളത് വളരെ ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള ഒരു കാര്യമാണ്. So here the condition നമ്മൾ നേരത്തെ പഠിച്ചു. H2 greater than 0, H3 less than 0, H4 that is the bordered Hessian greater than 0, less than 0 alternative signലാണ് വരുന്നതെങ്കിൽ it is the condition for maximum. It is the condition for maximum. See, why? If we have only 2 variables, we are considering only H2, that is considered as a bordered Hessian. But we are saying that in the question it is number of independent variables are there. Then it is generalized format. അതുകൊണ്ട് തന്നെ H2 greater than 0, H3 less than 0, H4 greater than 0. That means alternative sign ആണെന്നുണ്ടെങ്കിൽ it is the condition for maximum. Similarly, if H2 bordered Hessian 2, bordered Hessian 3, bordered Hessian 4 up to bordered Hessian n, everything is less than 0, then it is the condition for minimum. Now look at the answer. ഇനി ആൻസറിലേക്ക് നോക്കൂ. ഇതാണ് ശരിക്കും നമ്മളെ കണ്ടീഷൻ എന്ന് പറയുന്നത്. വെൻ വി ഹാവ് എ n number of variables. സോ ഈ കണ്ടീഷൻ വെച്ചുകൊണ്ട് ഇതിൽ ഏത് ഓപ്ഷനാണ് കറക്റ്റ് നോക്കും. സി H2 greater than 0 മാക്സിമത്തിന് വേണ്ടി ഫസ്റ്റത്തെ 3 ഓപ്ഷൻ കൊടുത്തിരിക്കുന്നത് മാക്സിമമായിട്ട് ബന്ധപ്പെട്ടതാണ്. സോ അതിൽ H2 greater than 0. So only this one, H2 greater than 0, H3 less than 0. So alternative sign ആണ്. So one is correct here. It is option 2. For maximum, H2 greater than 0, H3 is greater than 0. Now for minimum, see, for minimum everything that is bordered Hessian 2, 3, 4, everything is less than 0. See, it is the minimum, H2 less than 0, H3 less than 0. So everything is less than 0. For this is also correct. So 2 and 4 is correct. So 2 and 4 is the correct, that is option number 2. So option number 2, that is 2 and 4 only. So this is the correct answer, especially for, so Hessian determinant, higher order Hessian and bordered Hessian determinant, all these are the special determinant and special matrix, and it's very important concept, especially for the UGC NET examination, NET JRF examination. So ഈ conditions വളരെ important ആണ്, വളരെ important ആയിട്ട് നിങ്ങൾ by heart ചെയ്ത് പഠിക്കണം, അല്ലെങ്കിൽ ഇത് കൺഫ്യൂസ്ഡ് ആയി പോകും. അതുകൊണ്ട് തന്നെ ഈ കണ്ടീഷൻസ് Hessian matrixും ഹയർ ഓർഡർ Hessian matrixും അതുപോലെ തന്നെ ബോർഡഡ് Hessian matrixന്റെയും കണ്ടീഷൻസ് വെരി ഡീറ്റെയിൽ പഠിക്കണം. കാരണം അത് ഇവിടെ മാത്രമല്ല, നമുക്ക് ഫംഗ്ഷൻ ഓപ്റ്റിമൈസ് ചെയ്യാൻ, എസ്പെഷ്യലി അൺകൺസ്ട്രെയിൻഡ് ഓപ്റ്റിമൈസേഷനും കൺസ്ട്രെയിൻഡ് ഓപ്റ്റിമൈസേഷൻ കേസിലും, രണ്ട് കേസിലും നമുക്ക് ഹെസ്സിയനോ അതല്ലെങ്കിൽ ഹയർ ഓർഡർ ഹെസ്സിയനോ അതുമല്ലെങ്കിൽ ബോർഡേഡ് ഹെസ്സിയൻ ഡിറ്റർമിനന്റോ നമുക്ക് ഉപയോഗിക്കേണ്ടി വരും. അപ്പോൾ ഇവിടെ മാത്രമല്ല അവിടെയും നമുക്ക് ഇതിൻ്റെ യൂസ്ഫുൾനെസ് ഉണ്ട്. അപ്പോൾ ഇത് പഠിക്കൽ വളരെയധികം നിർബന്ധമാണ്, എസ്പെഷ്യലി UGC NET എക്സാമിന് വേണ്ടിയിട്ട്. സോ ദിസ് ഈസ് ഓൾ അബൌട്ട് ദി ഹെസ്സിയൻ, higher order Hessian and bordered Hessian. We will meet in the another videos. Thank you.